Okay, so this is the property, one sec, that we use here, for example. All right, so we have the fourth root of 32, right? We have the fourth root of 32. So what we're going to do is 32, right? Let me just write it over here. We're going to do a factor tree. You can divide 32 by 2. It's 2 times 16. And then this is 2 times 8. And then this is 2 times 4, 2 times 2. So if you look at all of the, the outer parts of this, we have all these 2's. We have 5 2's total. But if this is a fourth root, what we have to do is we have to combine them into groups of 4, and each group of 4 will come out as a single 2. 1 will stay, and that will stay inside the fourth root. Okay?
So you can't just write 2 root.
Yeah.
You can't just write 2 root 2.
No, because that would be a square root, but this is a fourth root. Okay, next, you have the cube root of d to the 7. Well, d to the 7 is just 7 d's, right? This is the cube root, meaning you can group them by 3's. Here's one group and another group. Each of these group comes out as a single d, so d squared will come out, and I have cube root of d left. Okay? Now, here too, the property that when you have even, odd still applies, right? Not to this problem, but while we're doing these, right? So like where you have to put square roots, absolute values. Okay, take a look at this next one. So now we have a square root of 12, which is what? 2 root 3, right? So the 2 will come out and the 3 will stay in here. Okay, C6, right? So here we're going to have c to the power of 3, which eventually should go in a square, in an absolute value. And then we have d to the power of what? Just 1. So which one needs absolute values?
Wait, no, just the d, just the c.
Just the c, because it has to be even, odd. Okay?
Wait,
why isn't the d in absolute values? Because you need absolute value if it was an even index, even power, and then you got an odd power. But here we had an odd power. Oh wait, this is, sorry. Oh my gosh, sorry. That's a, oh, sorry. Sorry. Here we have the square root of, one sec. Here we have the square root of d cubed. So how many d's do we have in there? We have 3 d's in there. 2 will come out as a single d, and then 1 d will stay.
Oh, but then,
Right, no need for absolute value. Okay, yeah.
But the c is all, there's no c's in there in the root because of the sole fact that you can take out.
Right.
Out.
Exactly. You can take out like even ones, yeah. Okay, next one. Okay, next one. 27, right? Cube root of 27, what do we get? 3. Okay, so here, let me show you a different way of doing this. So here we have an exponent of 4 and an index of 3, right? You can do 4 divided by 3, right? And what do you get? When you do that, 4 divided by 3, you get 1, remainder 1, right? Okay, so the first number is how many will come out. So for example, 1y will come out. And then the second number, the remainder, is how many will stay in here. So 1 will stay in there. All right, so here we have z to the 7. 7 divided by 3 is what? 2, remainder 1. So 2 z's will come out, z squared, and 1 will stay. And of course, you don't have to write y to the 1. It could just be y. Does that make sense? Yep? No? Yes? No?
Yes.
Okay. All right. So here, the same thing works with quotients, right? So basically, if you have the square or the root of a over b, that root can be applied to the numerator separately and the denominator separately. Okay? Now, if you have a root in the denominator when you're done, you have to rationalize the denominator and make sure that you get rid of any roots in the denominator. Okay? All right. So, if you have something like this, 1 over root b, right? This is a square root, right? How many b's do you need? How many total b's should be in here for them to come out as a single b?
Another square root.
Right, so there should be 2 total, right? You have 1 in here, that means you have to add another one. That's why we multiply by root b. Okay? So for example, this one you have 5 over root x. You multiply root x over root x. What you get is 5 root x over just x. Now, here, okay, if you have a different root, you have to figure out how many additional ones you need and multiply by that many. So one way of doing that is, if you subtract the outside number minus the inside number, that'll tell you what to multiply by. So, but again, I'm always against memorizing things. I just want you guys to like remember and like rationalize. Nah, you know, that's a pun. Like, you know, just sort of like, right? Like think about them, right? Okay, so take a look at this one here. What to multiply by? So whatever I multiply by, it has to be the 5th root of something because I have the 5th root over there. So now, here I have the 5th root of 4. Okay? All right. So there's a couple of ways to do this, right? What exactly do I have in there? Can I reduce it into a smaller base? What can I rewrite that as? This is 5th root of, what's 4 made of? 2 squared, right? Okay, so, okay, how many 2's do I have in here now? 2. How many should there be total for them to be able to come out? I need a total of 5. So how many more do I need to put in there? 3. So another way you can get that is 5th root of 2 to the power of 5 minus 2 is 3. Okay? So we multiply by 5th root of 2 to the power of 3. So that will be, in the numerator, 3 times 5th root of 8 over just 2. Okay? Yeah.
The second time you multiply by 5th root of 2 times to the power of 3.
Uh-huh. So first I didn't multiply by anything. I just like rewrote this 4 as 2 squared. And so, okay, I have 2 2's in there. I need a total of 5. That means I have 3 missing. So I have to multiply by another 3.
And then do you get 3 to the 5th power?
Right, well now I have together 2 to the 5th power inside the 5th root, so that comes out as a single 2. Okay?
And then the numerator is 3, is that 3 5th root 8?
Right, because it's 2 cubed. Okay, yeah.
What if the number inside the radical is prime?
Oh, then it just stays in.
Okay.
Yeah. Okay, let's do this. Yeah.
What is the point of simplifying 4 to 2 squared? Because you do have to find 4.
You can just add 4 more 4's, but then what ends up happening is you would have to like simplify top and bottom. You would have to reduce. You get additional factors of 2 in the numerator and the denominator, and then you have to reduce them. Okay, all right, so let's do this one. Always simplify to the like elemental base. Okay, so this one, you have the square root of a fraction. We're going to separate those. So square root of y to the 8, square root of 9x. Okay. In the numerator, what do I get? Y to the power of, how much? 4. Right? 8 over 2, 4. Remember, there is a 2 here, so it'll be 8 over 2, 4. It's a square root. Okay, here the square root of 9 is 3, but then that root x just stays there. But I can't have it there, so I need to multiply now top and bottom by root x. So I have in the numerator y to the 4 root x over 3. That just gives you an x. Okay? All right, now, similar, let's do this one. This is the cube root of 2 over cube root of 9x. Okay, you don't have enough of anything for not anything to come out here, okay? So we need to like simplify that. So what I'm going to do first is rewrite. This stays as is. This, I'm going to rewrite the 9 as its elemental base. Like the smallest base is 3 squared x. So now let's see what we're going to multiply by. Okay, cube root of, right? I have a cube root, so it has to be a cube root. Okay, so look, 3 out here minus 2 is what? 1. So I need 3 to the 1. Okay? Now, look at the x's. 3 minus, what do I subtract? What's the exponent of the x? 1. So 3 minus 1, 2, so it'll be x squared. Okay? So now I multiply by cube root 3x squared, top and bottom. So let's see what we're going to have. Here I have the cube root of 3 times 2 will be 6x squared over, look at what I have now. It's a cube root. Now I have a total of 3 3's. They'll come out as a single 3. How many x's do I have inside? 3x cubed. In a cube root, it'll come out as a single x. Okay? Let's do an intermediate step here. This will be 6x squared, and here I have cube root of 3 squared times 3, 3 cubed, x times x squared, x cubed. Okay? So now, when the index and this is the same, it'll come out as a single 3, right? 3 3's will come out as a single 3, 3 x's will come out as a single x. All right? Okay, so let's simplify a little bit more. Okay. So, okay, we always get asked this question, like, okay, how simplified is simplified? Well, so we're going to try to, break that down a little bit. So an expression is simplified when the index n is as small as possible. The radicand contains no factors that are nth powers of an integer. The radicand contains no fractions. No radicals appear in the denominator. Okay, so let's take a look at this. All right, so here, what I always try to do first when I have a radical times another radical is see if anything can be simplified on its own. Do I have enough of anything to come out, like can 100 come out of a cube root? No. It's just 10 times 10, so no. The a squared, not enough. Here, not enough, right? This is an example of where these two kind of like team up, and then, once they team up, like now something can happen, right? So I'm going to multiply those together. So this is going to be 5 times cube root of 100 a cubed. All right, so look, another way to do this is 5 times, oh, it's 1,000, sorry. Okay, so what's 1,000? It's 10 cubed, right? I'm just rewriting that. You don't have to, but I'm just rewriting it so we can all see it. So now this is going to be 5 times, how many 10s will come out? A single 10 times a, so that's 50a. So look at what we have here. Oh yeah, it's a cube root. Yep.
How do you get a cubed? You just take those at the a squared and the a.
Correct. You multiply them. Multiply the powers. Add the exponents. Yeah. Okay. So here we're gonna do the same thing. 6 times 4, those are the coefficients. They combine to make 24. And then here, this is a square root now. I'm going to get 16. C to the how many? 4. D to the how many? 8. So I get 24 times root 16, 4. Okay, so the C's, it's going to be 4 divided by 2. Remember the index is 2, so C squared. D to the 4. And none of those are odd, thank goodness. So let's multiply the 4 and the 24. That's what, 96? C squared D to the 4. And it's convention that we, like whenever you have like variables like this, we always write them in alphabetical order. Because math people are just orderly, you know? Okay, all right, let's do another one. Okay, when you have radicals that you want to add or subtract, these are similar to like terms. They have to have identical radicals for you to be able to add them. So for example, can I add 5x squared plus 3x squared? Yes, right? Can I add 5x squared plus 3x cubed? No. Similarly, with the radicals, you can add like a root 2 with another root 2, but not a root 2 with a root 3, right? So what you first have to do is simplify each of the radicals. So for this one, this will be 4 times root 8 becomes 2 root 2, right? Plus 3 times, how about the root 50? 50 is 5 root 2. So now look at what I have. 8 root 2 plus 15 root 2. Because these are the identical roots, I now have 8 plus 15, 23 root 2. Right? Okay. If I simplify, and I have a root 2 here, but a root 3 here, that's all I can do. I can't add them any further. Okay? All right, so let's take a look at this one. This is 3 times, how does the root 45 simplify? 3 root 5 minus 5 times. I know. No, 9 times 9 would be 81. Yeah.
Oh, it's
Huh?
4 root 5. It'd be 2 times 2 root 5, so 4 root 5.
4 root 5. Okay, let's see if that's correct. What you can do is this outside number, square it. What do you get?
And 16.
16. What's 16 times 5? 80. That gets you that. Right?
5 times 4?
4 root 5. So the way you can check is the outside number, you square it, you get 16 times 5 is 80. That's that number. Okay. All right. So then the 4 root plus 4 times how much? 2 root.
2 root 5.
Correct. Not really. Sometimes like 2 of them are the same, but the other one isn't. 9 root 5 minus 20 root 5 plus 8 root 5. So 9 plus 8 is 17. Correct. Okay? Isn't that fun?
Those are easier than the ones without in the section. If you go back out,
Yeah, these are a little bit easier. Okay, simplifying. It's just like, multiplying anything else, the FOIL system, right? First, outer, inner, last. So let's do this. So first, it's going to be 2 root 3 times root 3. The outer number, times 3.
Not just 6.
It's 6 root 3. Okay, the outer numbers will be minus 2 root 3, root 3. The inner numbers will be plus 9 root 5. And then the outer numbers, or the last one, will be 3 root 5 times root 3. So let's see what we have. 6 root 3 minus, how much is this? Minus 6, right? Plus, right, which is 6. Plus 9 root 5 minus root 15. And look at that. You can't simplify that any further. Right? Because none of those can be.
Wait,
It's 3 root 15.
Yeah, it's
3
3 root
root
15.
5.
it's three.
Because you have the 3 root 5.
Wait, what?
Yeah.
It's 3 root
Oh, this is 3. Sorry. Thank you. Okay? All right, so let's do another one.
Wait. Was it? Oh wait, never mind.
Okay, so first will give us 49 times 2. Okay, we're going to do that. We're going to be quicker on our feet this time. The outer ones, 7 times 3 is positive 21. Root how many? For the red ones, root 6. The inner ones, negative 21. Root how many? 6. And then the last ones, negative 9. Ooh, times what? 3. Right? So that's negative 27. Okay, so let's see what we have. 98. And this will be 0 minus 27. Perfect. Okay? All right. Okay, now these, these are my absolute favorite. Okay, remember how when we were talking about the imaginary numbers, the complex numbers, we said they had conjugates, the complex conjugates, remember that? Okay, so these also have their conjugates. So here, the issue is we have a root in the denominator, which we're not allowed to have. So I need to multiply top and bottom by the conjugate of whatever, of that denominator. So if this is the term, then I have to multiply top and bottom by the conjugate, which will be root 6 plus 5. So all you do, exactly, it's the imaginary. The only difference is with the imaginary numbers, we always just changed the sign of the imaginary part. Here, you're just going to change the sign of that middle, okay? All right, so top one also gets multiplied by the same thing. Oh my gosh, this is like legit one of my favorite things to do. And it's so much fun because like I haven't taught these in a while. So it's like I missed them. It's like that cousin that you only see like 2-3 times, like every like 2-3 years, and you're just like, oh my God, I missed you. That's how I feel. Okay, so let's distribute this. We're gonna get 8 root 6 plus 40. Okay. The denominator. This time I'm going to do it the long way, and then the next time we're going to do it using the shortcut. So if we FOIL this, first terms gives you 6, outer terms 5 root 6, inner terms negative 5 root 6, last terms negative 25. So I have 8 root 6 plus 40. These go away. 6 minus 25 is how many? Negative 19. And you can leave it like this. You don't have to separate them like we did with the imaginary numbers. Okay? Uh-huh.
Will the two middle terms, like of the FOILing, always go away?
Yes. And now we're going to use that to our advantage when we're doing the next one. So the next one, we're going to multiply by the conjugate of the denominator, right? Because it's the denominator's root that we need to get rid of. So what are we going to multiply by? Root 3 minus 4. Root 3 minus 4. Okay, so let's do the numerator. We got a FOIL. 6 root 3. So the outer one is minus 24. The inner one's negative 3. And then minus 4 root 3. Okay, the bottom one, we're going to use the shortcut, everyone. I have a plus b, a minus b. So what I do is I square the first one, right? I square the second one, and then I have to subtract them, though. This is from 2 chapters ago. A plus b times a minus b is a squared minus b squared. We've got to use the shortcut. In honors, I expect that you guys know how to do the shortcut. Remember, very soon we're going to have much bigger fish to fry. So this can't be the stuff that's like, tripping you up, right? So here, let me go on the bottom. What do we have? 6 root 3 minus 4 root 3 is how much? 2 root 3 minus 27 all over Is it?
Yeah.
9? No, 3.
3
Awesome. Okay. Okay. Now, that negative on the bottom, right? We ended up twice with a negative term in the bottom. This is an acceptable way to write it. However, conventionally, sophisticated math people don't like these like dangling negatives here and there, right? So we want to incorporate them. So sometimes what you might see happen is you can incorporate that negative, you can distribute it into the numerator. So what ends up happening is you have this and it becomes negative 2 root 3 minus 27 over 13, which means that'll be 27 minus 2 root 3 over 13. This is how people like to write it because, like the negative is not incorporated inside. It's just cleaner, right? It just looks cleaner. You know what I mean? No. There is no mathematical difference between this and this. No. However, there may come a time when you're taking a multiple choice test, right? And you don't know what form the answer will be in. Most probably, it'll be like this. Or let's say there is a math competition or something or whatever, right? Or you're checking your answer in the back of the book and you're just like, well, I didn't get it right. Miss Malikan, what do I do? And you're, right? So you got to be woke about these things. And you just have to know, like, these are all the same. Okay, yeah.
Isn't it like negative root 3 times negative 4? So why is it not plus?
Oh, shoot, that was a plus. Thank you. Sorry, this was a plus, so then what would this be? 10 root 3. Thank you. Thank you. All right. Yeah. All right. So next one, same thing. Let's do that. So we're going to multiply by root x minus 1. Okay. All right. I'll give you a minute to finish this one. Okay. All right. Did everybody get this? Yep. Yes. Okay. That's good enough. So look at the next one now. Is the next one the same or a different type of problem? It's a different type of problem. So to get rid of that one, it's just like having a denominator. It's like having 1 over root 3. You just multiply by the identical root, right? So I'm going to multiply top and bottom by root x squared minus 4. No, because now they're not separate. It's one root. So you have to multiply by the identical one. So in the numerator, we're just going to get the square root of x times x squared minus 4 over x squared minus 4. Nothing cancels out here. This x squared minus 4 can't cancel out with that x squared minus 4. And then, this one goes exactly with this number 60 from the last homework problem, right? If you have the square root of x squared minus 4, so many students want to say, oh, that just equals to x minus 2. No, right? You can't just take up the square root and pretend that they're the same, right? You have to keep it that way, and then that's how we would get rid of it. So the idea is no roots in the denominator. Okay? Yeah.
Why isn't it, on the numerator, why isn't it the square root of x times